Hey guys, Mr. McKinney here, just doing a review of Unit 2. So Unit 2 is all about the derivative. So we're going to talk about the definition of the derivative and differentiability, and then get into some of the rules that'll make your life a little bit easier. So when we talk about the definition of the derivative of any given function is an expression that's used to calculate the instantaneous rate of change or the slope of the tangent line at any point on the function. So keep in mind that the derivative is not telling you, like the derivative is not the slope. The derivative is an equation where if you plug in an x value, you can find the slope of the original function. Just a quick review of the notation. So if you start with a function y, you can say the derivative is y prime, or you can write it as dy dx, or you can say the derivative with respect to x of y, so d dx of y. All of these mean the same thing. If you start with f of x, then the derivative would be noted as f prime, or you can write it as the derivative with respect to x of f of x. All of these things mean the same thing. They're all just different ways of saying the derivative of the function. Now, if you see in the problem, use the definition of the derivative, or if you see the words difference quotient when trying to find a derivative, you're going to have to do it the long way. And the long way is basically just using the instantaneous rate of change formula from Unit 1. Because the derivative is essentially the instantaneous rate of change. So if I want to know the derivative of a function, and it asks me to use either a difference quotient or the definition of the derivative, then you're going to use the instantaneous rate of change formula just like we did in Unit 1. So for example, if I want to find the derivative of f of x using a difference quotient needs to tell you that you need to have a fraction, that's what quotient means, and difference means subtraction. And what it's referring to is this formula, difference quotient. So if you see a difference quotient, that tells you that to find the derivative, we're going to use the limit formula. So the limit as h approaches 0, f of x plus h minus f of x over h. So f prime of x, we have to keep the limit here until we can actually evaluate it. And until we get rid of that h on the bottom, we won't be able to evaluate it. So f of x plus h means just plug in x plus h here. So 3 minus x plus h squared minus, and then f of x is 3 minus x squared. So let's multiply it out and start simplifying. F prime of x, the derivative, is the limit as h approaches 0 of 3. If I multiply this out, I would get x squared plus 2xh plus h squared. I'm going to go ahead and distribute the negative to all those. So minus x squared minus 2xh minus h squared. And then just distribute the negative in here. So minus 3 plus x squared divided by h. You're almost always going to be able to cancel out the f of x terms with something from the f of x plus h. So in this case, the 3 and negative 3 cancel, and then negative x squared and positive x squared cancel. I'm going to go ahead and pull a factor of h out here, or you can just cancel it out. So I have f prime of x is equal to h times negative 2x minus h over h, and I already forgot my limit. If I had forgotten that on the AP exam, I would have lost credit. Now I can cancel these h's out. So f prime of x is equal to the limit as h approaches 0 of negative 2x minus h. Now I can plug in 0, and I'm not dividing by 0 anymore. So f prime of x is negative 2x. And since I've plugged in the 0, I don't need to write the limit anymore. Now, most of you guys are like, wait a minute, I know the rule. I can just use the power rule. The 3 goes away and the 2 goes in front. And that's a good way to check your answer. But if it says using a difference quotient or using the definition of the derivative, you will not receive credit unless you show the steps to go from the instantaneous rate of change. There's also a separate formula that you can use if you just want the derivative at a specific point. So if you already know where you want the derivative. Here I can plug in any x value I want. But if I know I just want the derivative at a specific point, I can use this formula instead. So instead of the limit as h approaching 0, instead of saying the distance between 2 points is shrinking, in this formula, you're saying that the 2 points are basically approaching each other. So you're picking your point A, and then you're having the function approach that. You can always do it this way and then just plug in your x value at the end, but sometimes this formula will be easier. This is all just notation. So if my original function is f of x equals 1 over x, and I want the derivative when x is equal to 4, I can write it as the derivative of y with respect to x evaluated at x equals 4, or the derivative of f of x, or the derivative of the function evaluated at x equals 4, or I can write f prime of 4. All of these things mean the same thing. It's just notation. It's getting used to the different ways that they might write the derivative. When we talk about the graphs of a derivative, so there's 3 things you should be looking at. If f of x is increasing, if f of x is decreasing, and if f of x is at a max or a min, which is when it's going to be at a mountain or a valley. All right, so if my original function is increasing, so for example, right here, my original function is increasing on this part of it, the derivative, f prime of x, should be positive. So I know that between here and here, when I graph the derivative, it should be positive. If the original function is decreasing, the derivative should be negative, because if it's decreasing, it's got a negative slope. And then if f of x is at a max or a min, then I should have my derivative equal to 0. So let's back up a little bit. If I want to graph the derivative, so let's say the original function here is f of x, and I want to graph f prime. I would start by looking at the mountains and the valleys. Wherever the original function flattens out, I know that the derivative should be equal to 0, because the slope of a horizontal line is 0. So now I just look at whether the original function is increasing or if the original function is decreasing. So when I look at the left side of my function over here, the original function is decreasing, which means that the derivative should be negative. So I know that the derivative is going to be negative until that first flattening out. From this point to this point, the original function is increasing, so the derivative should be positive. And then it's going to come back to 0 here. Whoops. From here to here, the original function is decreasing, so the derivative should be negative. And then from here to here, the original function is increasing, so the derivative should be positive. So if the original function is decreasing or has negative slope, the derivative is negative. If the original function is increasing or has positive slope, the derivative is positive. And then when the original function flattens out, the derivative is equal to 0. So those will turn into x-intercepts on the derivative. All right. And we'll come back to these graphs as we go through the units. A function is considered to be differentiable at a point if 2 things are true. First of all, the function has to be continuous. And the second thing is the left-hand slope has to be equal to the right-hand slope at that point. Now, in order to be continuous, keep in mind that there are 3 things that have to be true. So number 1, the function has to exist. Number 2, the limit has to exist. And those 2 things have to be equal to each other. And the way you'd write it in calculus is you'd say the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. This part right here is saying that the limit exists. Then you're going to say that it equals f of a. That part right there is saying that the function exists. And then since we're saying that they're all equal to each other, then we are saying that that last part is true, that a and b are equal to each other, that the function equals the limit. So all 3 of those things have to be true for it to be continuous. and then you check the left-hand slope and the right-hand slope. To look at the slopes, you're going to be looking at the derivatives. So when you're worried about continuity, you're looking at the original function. When you're worried about slopes, you're looking at the derivative. So if a question asks about differentiability, you're probably going to need to look at the original function to check continuity, and then to look at the derivative to check the slopes. So for example, on this piecewise function, is this function differentiable at 0? So let's check if it's continuous first. I think there might be an extra letter in there, but the limit as x approaches 0 from the left of f of x would be 0 squared plus 3, which is 3. The limit as x approaches 0 from the right of f of x should be 4 times 0 plus 3, which is 3. And then f of 0, I would use the bottom equation, 4 times 0 plus 3. So since the limit as x approaches 0 from the left of f of x is equal to the limit as x approaches 0 from the right of f of x, which is equal to f of 0, it is continuous. So now I need to check the slopes. Now, at this point in the unit, we had not learned the shortcut rules yet, so you would have used the definition of the derivative to find the slope, or you could have done the limit as x approaches 0 of f of x minus f of 0 over x minus 0. So you could use the limit as x approaches a formula, or you could do the limit as h approaches 0. Since this is just a review and we already know the shortcuts, I'm going to use the shortcuts. So the derivative of x squared plus 3 would be 2x. The derivative of 4x plus 3 would be 4. I want to know at 0. So the limit as x approaches 0, this is for x less than 0, x greater than or equals 0. So the limit as x approaches 0 from the left of f prime of x would be 2 times 0, which is 0. The limit as x approaches 0 from the right of f prime of x is 4. 0 is not equal to 4. These two are not equal to each other, so it is not differentiable. So the answer to this question is no. But the work that you would need to show, first you need to show it's continuous, and then you would need to show that the left-hand slope and the right-hand slope are not equal to each other. If the derivative exists, then we say the original function is differentiable. If the derivative exists for all x that are in the domain of f, then we say it's a differentiable function. Don't get too caught up on this vocab. The places where a function would be not differentiable, in terms of what it would look like on a graph, would be a corner. So if you have two linear functions that meet where the left-hand slope does not equal the right-hand slope, that's considered a corner if they're both linear. A cusp can either be a curve and another curve, or if you have a curve and a linear. As long as this is not true, so this is going to be true for any corner or cusp. Now, it doesn't really matter if it's a corner or a cusp as long as you specify that the left side slope does not equal the right side slope. Any discontinuity is going to make it not differentiable because one of the rules for differentiability is it has to be continuous. So if it's not continuous, automatically it's not differentiable. So you're looking at jump discontinuities, you're looking at infinite discontinuities, and you're looking at removable discontinuities. Any of those discontinuities means it's not going to be differentiable. The hardest one to see is usually a vertical tangent. So if you think about like the cube root function, at the origin, the tangent line is vertical. And the slope for a vertical line is undefined. Since the derivative is the value of the slope, if the slope is undefined, then the derivative doesn't exist. So a vertical tangent is another example of where the derivative does not exist. The last thing I want to talk about real briefly is the numeric derivative. When you see numeric derivative or NDER, it's just telling you to use your calculator. And sometimes your calculator will trick you. So So go back and rewatch those videos or email your teacher if you have questions. All right, that's it for part 1.